Very welcome, ladies and gentlemen. I'm happy to see you here in Stockholm, Sweden. In this cold and dark part of the year here in Stockholm. It's not the best season to visit this town, but I'm glad to hear that you're here anyway. And I think it's going to be a very interesting day. My name is Mats Lawan. Some of you might know me. I was trained as an engineer in engineering physics here in Stockholm at KTH, Royal Institute of Technology. And then I've been working as a science and technology journalist for like 20 years. And one of the things I've been following during these last few years is the technology developed by Andrea Rossi that we still are very interested to see how it will progress. So I'm soon going to describe the measurement procedure, but first I'm just going to tell you a couple of practical things. Outside here you will find bathrooms if you need. The coffee will be open until upstairs where you have some coffee and refreshments until 11 o'clock, and you're going to find some coffee outside here afterwards as well. So I'm going to do a presentation for half an hour, and then we're going to see the demo. You're going to have plenty of occasions and take photos and pictures and talk to each other. The whole session will be recorded on a movie, basically from there and with this camera here. And that movie is going to be put online later today. So if you don't want to be part in that movie, you should try not to be in front here. It's not live streamed. So the policy today is you can take any photos, any videos you want. You cannot come up behind here. Andrea Rossi prefers that you're not behind the stage here to take photos. But you can take any photos and pictures you will and videos, and you can publish them. But you cannot stream online live, because since we decided not to have this event streamed live, it's better that no one does that. Apart from that, there are no particular restrictions. So very happy to have you here then, and I'm going to describe a little bit what we're going to see today. I accepted the role as presenter and organizer of the event that Andrea asked me to take, under the condition that I would not be the supervisor of the measurements. So I'm going to explain that later. Anyway, the program of today, first I'm going to give you an introduction to what we're going to see and what we're going to do. Then we're going to do the measurements for about 1 hour. And we're going to have Mr. William Esferly here to oversee the measurements. He's a senior project engineering at Los Angeles Refinery Endeavor Corporation. And he's got a background trained as a mechanical engineer, background in nuclear plants and in refineries. Then Andrea Rossi is going to make a few calculations based on the results that we have measured. And after that, we are going to have a presentation of a theory work by Carl Oskar Gullström. Where are you, Carl Oskar? Here you are. Which I think will be challenging for most of you, but very interesting if you will be able to follow the details. So, and then after, we're going to have some refreshments and aperitivo at around 12:30 at 1 o'clock, depending on how long time it would take to do all these things. So, first of all, the ECAT QX reactor. It's describing it. It's the third generation of the patented ECAT technology that Andrea has been working with. And to describe it, I know that you have probably very different backgrounds here, so I'm going to try to make it as easy as possible. Basically, it's a heat generator, a heat source, built on a low-energy nuclear reaction, which is a family of reactions that are not yet understood theoretically. There is no good explanation which is widely accepted, but they are observed. And they were formerly known also as cold fusion, which is maybe not really accurate because we don't know if it's a real fusion reaction. So they're called low-energy nuclear reactions because they release an amount of energy. They have an energy density which seems to be at the same order as nuclear reaction as opposed to chemical reaction, which is about up to 1 million times higher energy density than chemical reactions, which means that for nuclear fuel, 1 gram of nuclear fuel for energy source corresponds to about 1 ton of chemical fuel. So that's the similarity with well-known nuclear reactions. But as opposed to well-known nuclear reactions, there is no strong radiation in low-energy nuclear reactions, which has not yet been explained in a good way. And of course, that's an advantage if you want to use it as an energy source, because the high energy density is the great advantage with nuclear reactions as energy sources. But the big disadvantage is the high amount of strong radiation. So this energy heat source is built on a low-energy nuclear reaction with a fuel based primarily on nickel, aluminium, hydrogen, and lithium, and with no radiation above background radiation, and with no radioactive waste. The claims of the ECAT QX reactor, the third generation of this technology, is that the volume of the reactor is about 1 cubic centimeter. The thermal output from one reactor, one piece of reactor, is between 10 and 30 watts, like a small light bulb. The input power is negligible, very, very, very small. The internal temperature inside the reactor is above 2,600 degrees Celsius, which is warmer than the hottest, or at the same order as the hottest normal incandescent light bulbs, halogen type. There is no radiation above background. And today we're going to have a cluster inside the heat exchanger that we have here. Inside here we're going to have a cluster of 3 of those QX reactors. The test protocol. First, let's look at the thermal output measurements. We have some water here that we're picking up with a pump and pumping into a heat exchanger where the reactor is inside the heat exchanger. So the water is going to be heated up and then pumped out into another glass, another plastic glass here. And we're going to measure the amount of water that we pump through with a scale. We have 2 thermocouples measuring the temperature. We're measuring the temperature before heating the water and after, just at the outside, at the output of the heat exchanger. And the formula we use is the well-known. The energy produced or released is the mass of water times the specific heat of water times the difference in temperature, the delta T. And the specific heat of water is 4.18 joule divided by grams per degrees Kelvin. And then we can calculate the average power energy per time by dividing the total amount of energy with the time that we have measured. So this is one way of measuring the output energy. The other, or the output power. Then we're going to have a second method at the end of measuring this. By the way, I should also say that we're going to start the real measurement when we have a stable equilibrium in the situation, so delta T is not changing. In the beginning, delta T will be increasing, but after a while, we're going to have an equilibrium situation, so we're going to have a stable delta T, which makes the calculations more straightforward. Secondly, we're going to stop using the water, cut off the tubes. In the opening here of the heat exchanger, we're going to use a spectrometer, which is an instrument measuring the different wavelengths of the light that we can observe. So we're going to measure the spectrum output from the quark QX, excuse me, the QX reactor, and we're going to do it only for like 1 minute or something, because it's heating up. When it's not cooled down by water, it's heating up, and we risk having a temperature which is too high. And at this moment, we're going to need to put off all the lights in the room here to measure the spectrum in an accurate way. So when you measure the spectrum of a black body, which this is similar to a black body is a kind of typical body emitting all wavelengths of light, for example, a normal light bulb. Then you have a curve like this, and on this axis you're going to have the wavelength, and on this axis you have the intensity. So you're going to see short wavelengths down here, and increase at a maximum of a certain wavelength, and then you have longer wavelengths going out here, and basically you're going to have all wavelengths in theory. And using a law that's called Wien's displacement law, you can take the maximum wavelength, and it equals a constant B divided by the temperature, or you can take it the background, and you're going to calculate the temperature by dividing B with a maximum wavelength. And the B is a constant, which is this one. Then from the temperature, we can calculate the output power using Stefan Boltzmann law, where the output power equals the area times emissivity, which is a number that we're going to put to 1 for this kind of measurement, times this constant called sigma, and times the temperature at the power of 4. So in this way, we're going to have another way of calculating the output power, and we're going to compare those two results, of course, and see if they're not going to be equal, but hopefully they're going to be at the same order of magnitude. So those are the two modes of measuring the output power. Then we need to measure the input power to understand if energy is really produced inside the reactor, or how much energy we actually produce and how much is coming from the input energy. And that's the electrical input. Now here we got an electric circuit in a series where we got, let's do it like that. We got a power source here, which is the white box, this one. Basically, this is a black box. So for me and for everyone else who is not the inventor, we don't know what's inside that box. But supposedly it has an output which is direct current, which is pulsed. So it's not alternating current, it stays above the 0 line, but it's pulsing. In series with the power source, we have the resistor with the resistance 1 ohm, which it's not necessary for the construction, for the functioning of the generator, heat generator, or for the system. It's only there today for measurement purposes. In series with the resistor, we have the reactor, and the claim is that the reactor has a very low resistance when it's in function. Basically, a resistance comparable to a normal conductor. Everything in series here. So you would say that the easiest way would be to measure the input power to the power supply here, the black box. Since the power supply is connected to the grid for having power from the grid. The problem is that the QX reactor produces lots of heat, which is conducted through the cables, and has a risk of disturbing or destroying the electronics in this box. So there is active cooling inside this power supply, which consumes about 60 watts, which is of the same order as the amount of power that we will see output from the reactor. So it makes no sense of measuring the input power to the power supply here. It wouldn't tell us anything. Then we have to do it in another way. The only measurement, basically, that we're going to do is measuring the voltage across the 1 ohm resistor with an oscilloscope. The good thing about this, which I think is good that Andre accepted, is that when you use an oscilloscope, you don't only see the voltage, you also see the waveform. And this is important because normally instruments like this one often have very great difficulties in measuring accurately voltage with strange waveforms, particularly if the frequency is high. So using the oscilloscope, we're going to see the waveform, we're going to see the frequency, etc. And with Ohm's law, which is that the current equals the voltage divided by resistance, we can calculate the current in this serial circuit. And the expected value, we don't know yet, but I was told that the expected value of the voltage is about 0.2, 0.3, 0.4 volts. So the current will be at the same, with the same number, 0.2, 0.3, 0.4 amperes. Now, for calculating the input power here, we will need to use Joule's law, which is power equals voltage times current. So we would need to measure the voltage across the reactor. Now, the thing is that Andrea explained that he doesn't want to measure the voltage across the reactor because it would reveal some particularities that could be very important in this phase of research and development not to reveal. So he doesn't want to measure the voltage across the reactor. So how do we do then? I mean, I'm an engineer. I don't like supposing things. I want to measure things. Supposing that the resistance in the reactor is very low is one thing, but I want to measure it in some way. So what we're going to do, first of all, we can combining those two laws, and we see that the power equals resistance times current squared. So if you have a very low resistance as a conductor, then you can have a very low power input power, which is the essential claim here. In this case, that you have 1 ohm here and a much lower resistance here. So most of the voltage will fall across this resistance and very little voltage across the reactor. So very little power will be consumed by the reactor. To make this, to understand if this is credible or not, to make an assessment, after the test of 1 hour, we're going to eliminate the reactor. And we're going to put a conductor there and see how the circuit behaves. So if we see the same situation as before, with the same kind of voltage across the resistor, so the same current in the circuit, that's one thing that indicating that the reactor actually behaves as a conductor. But we could be mistaken. Since we don't know exactly how this black box works, it could be not a fixed voltage generator, but a fixed current generator, maintaining the current at a number like 0.3 amperes, independently of the resistance in the circuit. So in that case, we could be mistaken. Let's say that actually the reactor does not have 0 ohm resistance or a very low resistance, but a high resistance. And you can actually calculate that with a resistance about 800 ohms with that current of 0.25 amperes squared, it would consume 50 watts, which is more or less the expected value of the output power. So in this case, if we're mistaken, if this is a current generator which maintains the current at this value, even though the reactor actually has a high resistance, the output power might come from the input power, electrical input power. And we want to make a conclusion if that's possible or not. So because of that, we're going to use another dummy resistance, take away the conductor there, and put an 800 ohm resistor and see how the circuit behaves. So if this is a current generator, we will see the current remain the same. And in that case, we will have a problem because there might be the possibility that the input power is actually the power that we measure as an output power. But if it's a voltage generator, on the other hand, we will see the current and the voltage across this 1 ohm resistor to be decreased by more or less a factor 800. And that would indicate that actually the black box is a voltage generator, and it would indicate also that the resistance of the reactor is low, is about 0 ohm, and it behaves like a conductor. So this is how far we could come. The suggestions of these two dumb resistors are my suggestions to Andrea, and he accepted them. I said that we can't just assume that the resistance of the reactor is so low. We have to, in some way, investigate it. And this is the way we're trying to do that. And at this point, I want to remind you, at least in my view, that this is not a scientific experiment transparent with all the details provided. It's a demonstration of a product by an inventor, and he puts the limits, of course, of what can be displayed and explained and provided or not. And this is the restriction of the situation, and you have to make your own, draw your own conclusions about credibility and transparency, etc. So this is what we're going to do anyway. So let's go back to the program. At this point, I have more or less explained what we're going to do, and I'm going to let you start the measurements, which we'll have about 1 hour doing these. So I'll let you just start. You can just start with the measurements at this point. And meanwhile, you are free to take photos and talk with each other if you want to go out and have some coffee or ask questions informally to any one of us here. We won't have any questions publicly today from the audience, but at the end I will try to ask a few questions to Andrea, which are some questions that I imagine that you all want to have some answers to. But that will be after this demo and after the calculations and the theory explanation by Carl-Oskar Gullström. So thank you very much so far, and enjoy. Anyway, I should add that we're going to have a camera up there which will take a photo of the instrument, of the computer, and of the oscilloscope. So you're going to see it produced on the screen here.
Yes. Some preliminary data. Here you see a pump. This is a water pump. This is calibrated to pump. It should be 1,080 grams per hour. Let's say 1 kilogram per hour. This makes things simpler because we will see the delta T that will be produced by the apparatus, and basically for each Celsius degrees that we gain, we will have 1 kilocalorie that will have been produced. So the calculation of the produced energy at the end will be simple. And so basically the flow that you are seeing now through that pump is of about 1 kilogram per hour. At the end, we will see exactly how many grams of water we will have pumped. And the other thing is that the temperature is measured inside that black basket that you see, where is the water that is pumped to the ECAT, that is this black cylinder that you see here. This cylinder is a heat exchanger. The ECAT is inside it. The ECAT is very small. We will talk about its dimensions later. All the rest is the heat exchange volume. So the water is pumped from that black basket at a rhythm, as I said, of 1 kilogram per hour, and goes in this transparent basket. This transparent basket is set on a scale. The scale will give us the grams of water that will have been passed through the heat exchanger. So we will base our calculation of the produced energy based on the amount of water that at the end of the test will have been pumped inside this container and the delta T. By the way, this vessel is graduated in milliliters, so we do not have only the electronic scale that is taking the grams, but we will have also the optical lecture of the graduated scale that you can see here in the side of the transparent vessel that looks at you. These are the basic things, and you will see from the oscilloscope the current. The current is a unipolar current. This is a current that flows in only in one sense and is pulsating, as you will see. These are the basics. This box is the control box that is a very complex things and has also a relatively very powerful cooling system because we have problems of overheating, while the energy erogated from the control box is sent to the ICAT by means of these two cables, this one and this one, that send the energy across the ICAT. At the end, when we will make the tests with the dummies, we will take off the ICAT and we'll close the circuit, making it continuous to see the differences using the same system across across a 1 ohm and an 800 ohm resistance. This is it. Now we start. Now we should see. You can see in the oscilloscope. Now the situation will go on with the temperature that will rise. Now, just to describe what is going on from the oscilloscope, you can see that the electricity that is supplied to the ICAT, in the oscilloscope you can read the energy that is supplied to the ICAT. Every square of that field is 100 millivolts, so 0.1 volt. You can see that the crest is, I mean, every segment along the y-axis is worth 100 millivolts. So you can see that when the energy is supplied, the voltage reaches about between 200 and 300 millivolts. I see now about 0.28 volts, 280 millivolts. And as you can see, all the energy is above the x-axis, which means that particles are moving in only in one direction. And the other thing that you can see is that we supply energy for 3 seconds, and we supply nothing. We stop the supplying of the energy for 4 seconds. So basically, the energy is supplied for 3/7 of the flowing time. In the meantime, you will see, while we go ahead, that the level in the basket, in the vessel, in the reservoir of the water that comes out of the ikat continues slowly to raise, and after 1 hour it will reach about the level of 1,000 grams. Il delta T 14, quindi qual era la temperatura di partenza?
Siamo intorno ai 21 e mezzo.
Cioè siamo partiti a 21,5? Now, let me explain to you what you are seeing in the graph of the temperatures. You can see that the water in the black basket, that is the water that is pumped from the pump to be sent to the ikat, is around 21.2 Celsius degrees, while in this moment we have reached at the output of the ikat 34.7. So the difference between 34.7 and 21.8 is the delta T that we reached so far. But still the curve of the temperature is not stabilized, so I expect that we will be producing more energy. Let me tell you that in this moment, should the temperature not raise even from now, we have a delta T of about 12 in this moment, because continues to raise. How much? 36 meno 21. Now, in this moment, we have 15 Celsius degrees of delta T, which, if the flow, as we will see, is 1,000 grams per hour, means that we are producing about 15 kilocalories. I remember for the non experts that 1 kilocalorie raises of 1 kilocalorie raises of 1 Celsius degree 1 kilogram of water. So basically, to raise 15 Celsius degrees 1 kilogram of water, we need 15 watts. And consider that the energy that now we are consuming, we will calculate later more precisely, but we are making about 0.3 volts across 1 ohm. Based on the law of, on the equation of Ohm, we have 0.3 volts and 0.3 amps. So the watts are 0.12. So we are consuming, in this moment, across the ikat, 0.12 watts, and we are producing, in this moment, 15 watts. And this is what makes interesting what you are looking. In the meantime, while we are waiting time, because now it is getting boring, because we will just see a curve going up. You know, but I don't know how to entertain you. But
I can ask you a few questions meanwhile, Andrea.
But before everything, I want of course you can, but of you can. But I want to say this. I want to say this. If today something will go badly, if something will fail, this will be absolutely and totally my responsibility. Because I have been the director of all this, my wonderful team has made a wonderful job, and I have directed, I am responsible for whatever happens in bed. No, in good, no, because apart the wonderful team that worked with me, I wanted to say that I have chosen this place to make this. I am choosing this place to make this test in memory of Professor Sven Kullander. No, it's not necessary. In memory of Professor Sven Kullander. And if today things will go well, I want to say this, that the encouragement that I got from Sven Kullander, the school, that the lessons that I got from Sven Kullander, and his enthusiasm is at the very base of this work. So if we did something good, has been for this encouragement. And I want to remind here this gigantic figure, because he was as much important as much humble. And his name, we did not forget his name, but I think it is correct to remember what he made for physics and what he made with extreme courage for in the sector of the LENR, because he has put his face on to give courage to anybody that worked in his sector from the high echelons of his science. I think this was very due to my friend Sven Kullander. This has been said. I am at your disposal.
Thank you, Andrea. It's very nice of you to make this dedication, I think, to Sven. We all remember him as a great scientist. I wanted to make some specifications. You told us about the consumed power. To be exact, that is the consumed power in the 1 ohm resistance. So still again, as I explained before, assuming that the resistance of the reactor is much lower than the 1 ohm resistance, the power consumption of the reactor is much lower than the power consumption that you mentioned, which is in the 1 ohm resistor, provided that the resistance of the reactor is very low. So now I also wanted to see at the image we see of the oscilloscope, by the division in the y-axis, we see, as you said, that the voltage is about 0.3, 0.25 volts. I was curious about the frequency division. If I read it correctly, I think every square is 100 microseconds. And my evaluation is that we have more or less 10 cycles per square. So every cycle will be like 10 microseconds, which would give us a frequency about 100 kilohertz. Is that more or less something accurate?
No, I prefer not to give information about this. You know, we are in a phase in which we are in a full research and development phase. And of course, I am here to give evidence of a result, not of a technology that in substantial part must be maintained in a confidential level, because for obvious reasons, because we are in a situation in which reverse engineering is extremely easy, and the only yes, this is patented, but but a patent litigation costs $2–3 million at the least for every country in which it is done. And the best thing is to defend until we are not able to produce massively this technology, putting the product in the market at a price that discourages any kind of reverse engineering or makes it not too much dangerous for us. We must maintain the secret of this technology stays in the particular play that happened, in the particular dialogue that is here between the control box and the charge of the ICAT. And correctly, Matsli once said that later then, when we will have finished the test, we will see the behavior of a dummy. Dummy is just a passage of current without the ICAT with the same system operating, and we will see the difference that is. No, it's going. It's okay. It's going. It's normal.
I can ask you a few other questions. One thing that I think is interesting to understand is the nature of these low-energy nuclear reactions in general, since many researchers have been working with them specifically since the announcement of Fleischmann and Pons in 1989. My impression is that the main difficulty to master or to have lower energy nuclear reactions running are three. It's the preparation of the fuel, it's the ignition of the reaction, and then controlling the reaction, to speak in very general terms. Could you give us an idea about which of these three is the most difficult one? Of preparing fuel, starting the reaction, and controlling it, maintaining it at a steady level.
They are not three different things. They are three parts of the same thing. And, it's like to say if what is more important to survive, the heart, the liver, or the brain.
That's a good answer. Thank you. So if I could take the occasion to ask some specifics of the reactor.
Thank you.
The maximum output power, if you say that you're not operating the QX reactor at maximum, to be careful.
No, because I am afraid that
it could burn.
It is working at more or less 30% of its capacity.
So the maximum capacity of one module, if you put it at the limit, it would be...
I will answer. I prefer to answer to this question when at the end we will make the calculation of the energy that we produce. But should we close this now? Should the temperature stop to rise right now? In this moment, what is the maximum T that we have? What is our T now, Fulvio, please?
39 gradi.
Now we have, say, 40 degrees. 40 degrees, say that we started at 20 degrees. We have a delta T. I cut the angles to make it easier. So we have about a delta T of 20. Should, from now on, the temperature not rise anymore, well, we would have obtained 20 watts. So we are making 20. Assume that from now on we go ahead until the end of the hour without further increase, minimum we have reached 20 watts. Now you are asking me, if I have understood well, correct me if I am wrong, how much it could have reached should I allow the maximum force? Is this the question?
That's right.
It would have reached about 60 watts. But these are words that I am talking, so is nothing. It has no value at all. It is just chatter. Now we will see where it will go. please take for good only the data, not the data that I could have made, but only the data that I made, because otherwise I could also not bring here all this stuff, but just say, all right, guys, I got 60. What we are doing is what we are doing. Let me be pessimistic and assume that we will not raise anymore the temperature. The ratio between energy produced, which is 20 times 1 point, if I am not wrong, 1 kilocalorie corresponds about to 1.16 watt hour. But so let me say 1.1. So basically, we are making 22 watt hour per hour if this does not raise anymore. Well, if we are consuming 0.12 watt hour per hour, we are making 20 watt hour per hour, as the situation is right now. If it raises, the ratio will raise in proportion.
How much was the flow? Can you repeat?
The flow is 1 kilogram per hour, as we will see at the end. Oh, by the way, the scale there is of Matzlevan because he did not trust my scale, and the vessel is of him, so the graduate scale is granted from him. I am just joking. At the end of the hour, I am sure you will read about 1,000 grams. Should be something more 1,000. I calculated 1,080. Let's just assume 1,000. Let's tie it down. And
could I ask you some questions about specifications? For example, the control box, which is quite large now, how small do you expect it to be?
The control, this is a very interesting question, which connects with the industrialization. This box now is, we have a very big problem of overheating. And so this box, most of this box is designed to cool down. And most of the energy consumed by this box is to cool down. And there is a big technology to cool down inside here, because it is not so simple as at this appear, because we have a time at our disposition to put down the temperature that is very short. So it is not that easy. I put in contact a cold thing with a warm thing, and it cools down. Yes, but it takes time. During that time, we have components that burn. And this has been a big problem. I am pretty sure. Now, we are in contact. I cannot say the name of the concerns we are in contact with.
Corporation, you mean? The name of the corporation?
Yes, corporations. But I am sure that with their power of fire and with their technological capacities, we will have a reduction in costs and dimensions that will be very remarkable. Now, the dimension of the cat is already very, very small, because you consider that the cubic centimeter, of which correctly Matzlevan has spoken before, is the volume, not of the reactor, is the volume of the reactor plus the space, the volume necessary to expand the heat exchange. Because the real dimensions of the reactor are 0.08 millimeters of diameter and 0.6 millimeters in length. This is the real dimension of the reactor. And with these dimensions and the consequent density of energy, many things can be done. But basically, this white box that is an aerator, this is to keep cold all the system, etc., can become, if we resolve the problem of cooling down, as it is just matter of time, and it will become, no, non toccare, do not touch, please. Mats, you cannot stay there, I am sorry. Go to your place, thank you very much. At the most you can put the finger in the water to be sure that it is not cold, but that the most. So I was saying that these can be as big as a packet of cigarettes, but not just for one ikat, but for thousands of them. But to make this, you know, we need an engineering capacity that presently we do not have, but that we are struggling to get by the right alliances. Okay, now it appears that the curve is stabilized. So from this moment, Mats, you can calculate from this moment it is not gonna go much up. Where is it now, the temperature?
39, salta dai 39,2 ai 40.
Okay, we have about 40 Celsius degrees of delta T, and
so let's measure the weight now, or should it be empty?
Yes, very good. Empty. Fallo tu.
L'acqua base, la riscaldiamo.
Ah, già, giusto. No, we must empty it in another vessel, because if not, we heat up the water. Yes. Fallo tu, Fulvio. Fallo tu, Fulvio. Levalo. Eccolo qua. Sorry?
Guarda, già fatto, un grammo. Quello parte facendolo così. Il problema è quando ripassiamo, quando arriviamo a un litro, dobbiamo va bene, scuoteremo questo, poi dentro.
No, no. Matsruan broke the water. Yeah. No, it's not. No, could be water and alcohol, for example. It heats up more if you put alcohol. Yes, because the boiling point of alcohol is 775 Celsius.
Andrea, per dimostrare che non usiamo liquidi speciali,
sì,
alla fine bevine un po'.
Bevila tu.
Se mi paghi abbastanza la bevo io.
Yeah, yeah. Io sto dando numeri bassi.
Abbassiamo, no? Non ci serve fare i fuochi artificiali.
You are absolutely allowed to take pictures. The only thing I pray you not to do is go in direct stream in the internet, because we don't like it. But you can take pictures, you can take also movies for you, no problem. Just do not go live stream in the internet, please. I trust you. I just trust you. I should have to say no phone call, no phone, but I trust you. Just don't do it.
Te la regalo. No, te la regalo. Mazzi. Porti a casa, conta e il blocchetto di legno, poi ne fai un altro qua. Poi usa la fotografica. No, tieni come ricordo. La tieni come ricordo. La costruzione si può lì. Non toccare.
Molto bene, complimenti.
No, I heard. We should not ground them. So, nice to meet you too.
We're at 1 hour.
1 hour? Okay.
All right?
Plus or minus.
I didn't have you use a
This is
stopwatch.
plastic cap, come on.
What is the temperature?
It went up 19 degrees.
Anywhere.
This is for the X, this is for the one. The answer is 20.
Ladies and gentlemen, if you could take places, sorry, we're soon ready to conclude the measurements for the heated water. Before we do that, I would like to make a couple of clarifications.
Che io faccio la coppa prima con l'acqua e poi senza l'acqua e vediamo quant'è l'acqua prodotta.
We were discussing a heat problem for which we're using or Andrea is using the cooling system
Spegniamo il sistema e facciamo...
in the control box.
Avverti che sto spegnendo.
Yeah, just a moment.
Aspetta.
So the heat problem with heat coming through the cables from the reactor was a former problem. Andrea explained to me that he has resolved. So the heat problem is inside the control box. And that's where he has the active cooling which consumes power. So it's not a problem any longer with heat from the cables. That was a former problem. Now we have concluded the warming phase of water, and we're going to stop
I stop in this moment.
yeah. And William, you have taken all the measurements, all the values, so we're ready? Should we?
Questa è l'acqua prodotta.
Okay.
Dopo la misuri quanta ne vuoi, la travasi, la misuriamo.
See,
Ok?
we're going to measure the water afterwards. We can measure the weight now,
Ok?
right?
Aspetta, devo spengere la pompa.
Ah, okay.
Deve spengere il reattore, fare la curva di discesa e poi facciamo il resto.
We have to turn off the pump first and the reactor. So, okay.
I go?
Spenge
Yeah.
il reattore, facciamo la curva di discesa e io spengo la pompa.
So
Facciamo la discesa.
then he cut off the reactor now?
The reactor has been turned off. Now you will see the curve going down. If the curve remains up, that would be very suspect.
So by the way, you don't have any possibilities of making a self-sustained system with this reactor?
Well, this reactor has worked, as you have seen, for 3/7. This reactor has worked for 3/7 of the time. Has been fed by 3/7 of the time. So this means that for 4/7, which means the hour is 60 minutes, for about 25 minutes. 25 minutes it has been fed, and for about 35 minutes it is gone without feeding. But as you will see, the ratio between energy produced and energy consumed is so high that the distinction between self-sustaining mode and non-self-sustaining mode is very subtle.
And there was some concerns about measuring the temperature before the pump and not after the pump, but there are two ways to address that. The first one is that we can see that the temperature remained low before starting the reactor, even though the pump was working. And the other way is Andrea told me that he's going to give the pump to me afterwards, so can I put it to pieces and discover if there is anything hidden inside?
I will give as a gift to my friend Mats Luan 2 issues that are important under this point of view. One is the pump, so he will be able to disassemble it and check that it is just a pump and not a heater. The second, which is important, is this block that connects the reactor to the reactor to the. Somebody could say, what is this block? This is a block of wood. So I will give also this to Mats Lewan, so he will have it.
Then one thing that I forgot to mention during the presentation is the claim that the plasma inside the reactor is a neutral plasma with equal amounts of negative and positive charges moving.
Yes, I discovered this with a Van de Graaff generator. I have made, with another device, not this, I have made a longer plasma with a Nicata designed specifically to make that measurement. And then I have put in parallel, so I had the beam of the plasma. Then I have put a Van de Graaff generator in parallel, putting the ball of the handle and the line that goes across the ball of the handle and the sphere of the van der Waals parallel to the axis of the plasma. You know that a Van der Graaf generator moves electrons, and this cascade of electrons is obviously a negative beam. Should the plasma have a prevalence of minus sign, it would be arched in rejection of the negative source that comes from the Van der Graaf. Otherwise, should the positive particles be prevalent, it would arch toward the Van der Graaf. I have noticed that it stays straight, so that it is not even vibrates. So it is absolutely not affected by the negative field that I have put in parallel of it. From this, I have concluded that it contains plasma is a soup of free electrons and protons, and I'd assumed that probably the number of protons is the same of the number of electrons. Maybe wrong, but this is a fact. It does not arch in parallel with a negative field.
And one last question, Andrea. You also mentioned the dimensions of the plasma, which is, as far as I understand, there is a light inside the reactor, which is fairly this size, a few centimeters, but the real size of the plasma is much smaller.
Yes, it is about 0.6 millimeters in length and 0.08 millimeters in diameter.
Okay, so it's a really small grain. I mean,
like a piece of hair.
And you measured that, you told me you measured that in what way?
Yes.
With what kind of instrument did you measure that?
The spectrometer. But use it in a completely different way that we will use it today. Oh, by the way, another thing. The signal that we will get today, right now, because when you give me green light, I proceed to the spectrometry. The signal that you will read now will be very dirt, because it is not a perfect situation in which I have the plasma and the eye of the spectrometer in a completely neutral field. This will be a very approximative situation, because I will just cut this rubber pipe of water, because now we do not need it anymore, because we are not going to do more calorimetry today. So I will cut it with a scissor and will point the eye of the spectrometer inside here. But it is dirt now. It is dirt, it is wet, there will be many reflections. So we will not see a perfect black body signal as in a pure situation. We will see many peaks. And to be conservative because now we are calculating the energy that actually is produced inside there, no more by calorimetry, but with the constant of Wien and with the Boltzmann equation. To make this, we need to know the temperature with the constant of Boltzmann divided by the wavelength. Obviously, the longer the wavelength, the lower the temperature, because it is 2900 divided the wavelength. So the higher the wavelength, the lower the temperature, and then the lower the energy, because in the equation of Boltzmann we will bring the temperature, elevate it to the fourth power, and etc., 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 as we will see. To be conservative, we will choose only in the spectrum. We will choose only the longer wavelength, and we'll calculate based on that. we will choose the prevailing waves in the right of the spectrum. Again, you will not see. This is a spectrometry made to make a demo today where spectrometry has a marginal importance. Should we have to do accurate spectrometry, this is not the correct system to do it.
Can we proceed?
Yes. If you give me green light. Allora, prima spengo la pompa e te la do.
Pompa spenta. Aspetta che il prendo.
Questa è l'acqua.
Che faccio? Sfido il manicotto?
No, taglia che lo diamo tutto.
Attento che adesso si svuota. Mi dai?
Ah, vediamo ancora questa. Questo. Adesso qui non c'è elettricità, no? Tutto staccato.
No, tutto staccato. Questo è stato svuotato.
It went a little bit after. So it was right around 1,000.
Yeah, but this is with the container. So, maybe the container. When
No, fill with this. Because possible have more plastic.
that's zero.
It's zero? Okay. How much water you have produced? 996.
Mats,
Yep.
Questa te la tiri addosso.
questa è tua.
Gift for you.
Grazie.
Prego. Una cosa in meno da portare in valigia.
Ah, no, beh, è sotto. Questo l'abbiamo fatto, questo l'abbiamo dato, questo adesso serve moltissimo. Sì. Allora adesso spettrometro.
C'è ancora acqua.
Non è che... Andrea, c'è un goccino d'acqua ancora nel reattore. Dentro il reattore c'è ancora un goccino d'acqua, conviene che lo giri un pochino per farlo uscire.
Okay, how many seconds? Is there anything you would like me to tell your family?
Devo puntare questo occhio deve andare a vedere qui sopra. Questo occhio. By the way, an important thing for some of you can be this. We have used oscilloscope Tektronix model TBS 1052B, as in Bob. The probes that we used are K probes supplied by Professor Bo of the Uppsala University and calibrated by him. The spectrometer is a stellar green wave 16 made in the USA. That's all I know.
Io non so quanto lo voglio mettere, non ho proprio idea.
Now, it's not easy because now we have, with the eye of the spectrometer, try to center the channel that goes to see the plasma. It is not. I was saying that the difficulty now is to center as much as possible the eye of the spectrometer that is here, exactly this one. It looks from up to down, and now I have to try to set it as precisely as possible upon the plasma.
Posso?
Questo è gomma.
Gomma. Ma questo è alluminio.
Allora io metterei qua sotto una base.
No, invece tu dovresti fare una cosa. Metterlo questo un po' così, e tirargli questo così, in modo che gli punta dentro. Capito? Allentiamo di qua e tu glielo punti dentro. Se mi fai guardare nel buco, ci provo.
Sai cosa? Si può usare una penna.
Guarda Andrea, è dritto per dritto.
Perfetto, l'hai puntato? Perfetto.
Poi.
Questo è fermo, quello è fermo. Adesso lo colleghiamo. Adesso aspetta perché prima devo calibrarlo. Allora adesso prendiamo il computer. Questo è il collegamento.
Mettilo sopra il computer mio, dai.
I need the technician that in a few minutes I will need total dark area.
Are you ready here with connecting the spectrometer?
I have to calibrate before.
Okay. Poi lo spettro si vede sul computer.
Sì, però non ho più il buio. Questo è il problema. Sì, vabbè, sarà uno spettro molto scuro. Perché ovviamente se tu lo vedi nel computer io non ho buio, se non ho il buio non ho lo sai. It will be, you know, a spectre a little bit fat, because now, to allow you to see the spectre there, I cannot the dark. But to get the spectre precisely, I need the absolute dark. So again, we are going to make something that is very approximate. I have to tell this because an expert of spectrometry could be very critical about what I am doing. I am just adjusting the things. So we will be very conservative and we take only the higher wavelength. But here, the absolute dark will not be. At that point, the spectrometer will do what it will do, what will be able to do.
Do you need to get off the lights now, or?
Not yet. Not yet. Maybe in 1 or 2 minutes or 3. Now I have to make up. Now I need full dark. Buio totale.
Kan du skärpa där innan du... Un attimino. Il focus. Okay, no, we can just take a use it.
Okay, now you can see that we have.
Andrea, parla nel microfono.
Oh, sì. Now, I would say that the peaks, the more the peaks in the far right are around 1100 nanometers, which means here the number in the x-axis are nanometers. And so we have a massive amount of peaks between 400 and 600 nanometers. But the signal is very dirt, So I would say that we could pick the last peaks in the far right, which is 1100. That I must tell you, when the spectrometry is made properly, I get the peaks, a clean peak at 1.1 micron, which is 1100 nanometers. Now the signal is pretty much dirt. So if you allow me, I will make the calculations of the energy at 1.1 microns, because if I take the peaks that are shown now, I would have an absolutely over-evaluated value. As you can see, we are not in the dark.
Il reattore è spento.
Cosa è spento? Il reattore è spento. Oh, che stupido, sorry.
So we had to start the reactor, of course. It's one essential piece of the...
Lo fai andare in continuo?
Of course, now I can turn on the reactor for a very short time because I have not cooling.
Mettilo in continuo, fallo partire. Andrea, fallo partire e adesso c'è. Ecco, è alimentato. Si è spento, ecco, si è acceso. Si è spento. Aspetta, si è acceso, ecco.
Okay.
Lo metto fisso.
You know, it sees in the left there are the same signals that we had with the reactor turned off. So I would take this peak here that you see here, around 1100, that is the real one.
Perché non è nel Andrea,
See? I had to turn off because now it is overheating.
questo lo devi mettere fisso. Come lo metti?
Bisogna mettere, basta mettere qua, metti 10.000 qua, metti 10.000 qua, massimo 10 secondi, se no qua non lo sento.
Sì, adesso lo metto, lo devo vedere per cercare.
Io non accendo fino a quando, perché se no lo bruciamo. Vuoi venire a centrarlo tu? Aiutarti a centrarlo.
So there are several concerns. One concern is...
Can I have light anymore?
No, lo devi accendere tu, questo
Yep.
lo accendi, lo accendi.
One concern is that the spectrometer is not centered on the eye, on the opening of the reactor capsule. And the other concern is that the reactor cannot be switched on for a very long time without cooling.
Sono infilato questa sonda nel tubo. Ho paura, no, si prende una botta di caldo, la rovina. Ah, ok, perché quella è una fibra ottica.
E tenerlo a mano lì, nel buco, tenerlo così, all'apertura.
Ho paura di bruciarlo, ho paura di rovinare l'occhio, perché non c'è la difesa lì, capito?
Neanche tenerlo qua? No, vabbè.
Possiamo anche provare a fare
Quelle
così.
sono fibre ottiche.
Possiamo provare a fare così.
Così.
Facciamo così, solo per un attimo. Tu lo tieni, allora ci vuole. Tu lo tieni, io vado a regolarlo.
Dovresti vedere che sia dritto.
Yeah. Only
Lo puoi tenere più
few
vicino.
seconds.
E non è centrato. Dal mio punto di vista è qua. Centrato lì. Tu vedi da lì.
Ok, sarà breve perché qui siamo proprio vicinissimi.
Ok. Quando accendi, è acceso il reattore?
Il reattore non è acceso, no? Siamo pronti?
Sì.
Allora,
Giù le luci,
Le luci devono chiudere.
un
giù le
attimo.
luci e dopo accendo. Giù le luci e dopo
Aspetta, prima si spegne.
Sì, ma c'è luce. Vado?
vai.
Adesso va meglio.
Still. Ok, stop, basta. I take I take the 1.1 micron, which is here. Stop, basta. Stop. Stop, because we are burning the cat now. Because I have not the coolant. I have not the coolant, so I cannot stay longer. Okay. As I said, the signal of the spectrometry is not good because it is not dark. Here, we need the full dark to have a spectrometry that is worth something. So, at this point, I just can tell you that with a proper measurement, the wavelength is between 1 micron and 1.1 micron. And so, making at this point 2900 divided by 1.1, we have 2636 Kelvin, sorry, because it's in Kelvin, Kelvin degrees. Then, once we have the temperature of 2636 Kelvin degrees, we go to the Boltzmann equation, where watts are equal to sigma time epsilon time t to the fourth time. Did everybody hear what I said, or I have to repeat it? Yes. So I repeat, once we had obtained with the Vienne equation the temperature of 2636 Kelvin, at this point we go to the Boltzmann equation, where watts are equal to sigma time epsilon time t to the fourth time area, wherein by substitution it becomes 5.67 time 10 to the minus 8, that becomes minus 12, because later we will consider the area in square centimeters and not in square meters. Time 1, that is the epsilon, is the emissivity. Time 2036 to the fourth becomes
becomes a 4.8 times 10 to the 13th, and then time the area of the reactor, that is 0.08 times 2 times P times 0.6. Believe me, the final result will be about 70-71 watts, which is higher than the energy that has been calculated by calorimetry, but this is obvious because in the case of the spectrometer, we go to see the real energy and the 100% of the real energy that is inside the plasma. While here with calorimetry, we have been able to measure only the thermal energy that has been exchanged between the reactor and the heat exchanger. So the heat passed from the plasma through the wall of the heat exchanger, through the water, and then we had obviously losses here, etc., etc. So the efficiency of the calorimetry is enormously minor than the energy measured directly by spectrometry. But in any case, even with a high efficiency heat exchanger, it is impossible to reach an efficiency equal to to get all the energy that is inside the plasma. Sorry for the very approximative. I just wanted to try to do something, but unfortunately we did not have the dark, and so we did not have a spectrometry. I have described to you what I have discovered. That anyway does not affect in any measure the calorimetry that we made before. Well.
So thank you, Andrea. Before going ahead with the program, we should just do the measurements with the dummy resistances. So at this point, we need to detach the reactor. Is that so?
Yes.
And if we close that computer, we can have the telecamera on this one. Can we close that one? Kan du ställa in kameran? Du kan sluta spela in, du behöver inte spela in.
Sono lì, vicino ai telefoni.
Du kan ställa in kameran igen på det där instrumentet som den där. Alltså.
Okej. Och ska jag spela in den då?
Nej, det behöver du inte.
Sì, lo switch.
And how much did you get?
Aspetta, lo switch.
Okay. Okay. And how much time? So did you divide by time? By second?
It's, lascia.
Yeah, the total energy divided by how many,
Okay.
in how many
Questo,
seconds?
Andrea, hai fatto tutto da solo.
79,102
Pigliatela con te stesso.
600. To get the watts.
Vabbè.
Watts,
what I mean?
watts is 300 milliamps.
No, the watts out. Watts out.
Fatto.
What's that?
0.09 watts.
79
Non abbiamo uno strato per l'acqua.
divided by 3,600. So it's 22 watts.
Yeah, 20.
Oh yeah, right. So there you go.
Yeah, divided by the input, 0.09.
Yeah, but then it's virtual because that's the input power of the resistor. think, and then probably the reactor, if we can confirm that the reactor is a conductor, is even less. That's something that Oh yeah, we're going to start. Yeah, right. We can do that. We're going to start with the conductor. Andrea, dove che mettiamo? Il circuito?
Vieni.
No, ma il circuito dove che lo mettiamo?
Sta qui.
Calma, adesso...
Hai già messo, ecco.
Te l'ho già, Andrea.
Hai già...
Ho già giampato il reattore.
Okay.
Ok, allora facciamo...
So what we've done here is that I don't know if you can see the two cables that were attached to the one side each of the reactor are now at one same point. So basically we disconnected the reactor and it's one circuit going in serial with a 1 ohm resistor. So if you touch the oscilloscope to the 1 ohm resistor again to measure this one over here, yeah. We got patience? And then you can just switch on the control box, is that so?
Sorry?
Can you switch on the control box, is that so?
Ready everything?
Cosa devi attaccare? L'oscilloscopio, la resistenza?
Attacchiamo l'oscilloscopio. Se attacchiamo l'oscilloscopio è grosso ma non male. Everything is right? Go.
Ho invertito i qui. Uno, due, tre, quattro.
0.4 volts.
Vai. Guarda,
0.4 volts.
questo è diviso 100 millivolts, 100, 200, 300, 400 millivolts.
Yeah, so basically we got, although the waveform is not as pulsed as before, it's different because probably the control unit reacts differently when the reactor is not there. But the voltage is at the same order of magnitude. The division here is 100 millivolts and we're about 3 or 4 squares, about 300 millivolts, whereas before we had like 280 millivolts. So in that case, the voltage across the resistor is now a little bit higher. So that would mean that maybe my quick conclusion would be that the reactor would have a resistance which is slightly higher than a conductor, very little.
No, we're working with some feedback.
Yeah, might also be. Anyway, it's same order of magnitude.
Feedback from reactor and the system. No giving you.
Yeah, now we can switch our input.
We're reading the hardware from reactor for make the wave for solicitation.
Yeah.
No feedback, no work.
Yeah, so this is the 800 ohm resistor.
Lo vuoi in parallelo, in serie, come lo vuoi?
In serie, invece del reattore.
Dammela, la bolletta. Mi spegni, non mi voglio.
We can check this resistor, which would be 800 ohms, right?
Vuoi provare questa resistenza? Cosa vuoi fare? No, provare questa. Quanto scusa, sei un ingegnere elettronico?
Can we see that one? Here.
798.
There.
Why point 06?
Yeah. Because it's 2 kilo. Here it's 2 kilo. The range is 2
I
kilo.
need to make this question.
That's good. So this is 800 ohm. This is an 800 ohm resistor.
Serious?
Yep.
Okay.
So now I got the 800 ohms resistor instead of the reactor. And we have to, did you start? Yeah. Yeah, we need to change the range of the oscilloscope if it's not visible from the start. Yeah. Yeah, so here it's about, I would say, 10 millivolts. It's 1/10 of a, if you change the range, now we got, the division is 20 millivolt, and we got,
Andrea, una serie, una serie. Can I use your? Ingresso della serie e uscita della serie. Ce l'hai? 11,53
11,53 volt.
volt.
Sì. Sono volt.
Sì, quando scala a 20.
okay. And that's the voltage across what?
The 800 plus 1.
So that's the total.
11,53.
Okay, that's the total voltage. And the voltage across the 1 ohm resistor you're measuring with this one.
Yes, exactly. I show you.
Mm-hmm.
You want total?
No, it's fine.
Why not? Okay, total is, wait, 1 and 2. And you can see we go to
We must change range now.
out of scale.
Yes.
It's off. It's off. 10 volts. If you want, I Sì, Andrea, li stiamo leggendo i 10 volts. Tranquillo. Adesso run.
Which means that in this case, when we have a large resistor, a very small amount of voltage falls across the 1 ohm resistor, whereas during the experiment where we had the reactor, most of the voltage fall across the 1 ohm resistor.
La tensione che vedevi sull'oscilloscopio era la tensione alla resistenza da 1 ohm. Lui mica mi ha detto di guardare l'intero sistema. L'intero sistema l'abbiamo visto con questo. E questa adesso è la copia perché l'abbiamo messi qua.
Perché lui segna con una scala di
Vedi,
10
adesso è
volt
tornato a 0.
a 0 e 11
No, è
volt.
11-12.
È 11-12 nel totale. Sì, perfetto.
So the total voltage, to the system is 12 volts. It's about 12 volts.
Yes, and here yes.
Lavoriamo con 12 volt.
Even,
If we make 12 volts divided 800 ohms,
yeah,
per the amps.
yeah, sure. So also during the experiment, do you have 12 volts as the active voltage in the system?
We start from the continuous current, 12 volts, and after we generate a control wave in front of the answer from the charge. I can tell you more.
Could you please measure the voltage over the 1 ohm resistor again?
With what instrument?
With the oscilloscope, yeah.
This is type of pulsing is because No, 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 no.
So it doesn't really have the same character as during. Can we take away the? Maybe this is disturbing. It doesn't really have the same shape as during the experiment, of course.
The millisecond is the same.
Yeah.
Have a similar, not the same, because it's not driven.
So. Whereas during the experiment we had a voltage about 300 millivolts, now we got about, let's say, 10 or 20.
50, 10, but double is 20, 25.
Okay. I would expect it to be divided by 800, but...
Depend from the feedback of the electron.
Okay.
No field charge, no field.
Okay.
No give us.
So,
It's not a simple.
ladies and gentlemen, should we conclude the measurements and the calculations and let Carl-Oskar Gullström make his presentation on the theory? Vi behöver ett headset till honom. Ja.
Okay, so the data collected by the engineer are these. Basically, you have seen everything already. Anyway, the mass of water that passed, sorry, I don't understand your calligraphy. The mass that passed is 996 grams. So the mass that passed is 996 grams in 1 hour. And therefore, multiplied by 4.18 joules, it gives to us 19, sorry, I don't read. We have a delta T, so we have 1996 grams. We have a delta T of 19 Celsius degrees. From a simple operation, we have that the energy out has been 79,102 joules, and therefore we have about, what is written here?
324 joules in, or 0.09 watts.
So at the end, sorry, but I use, so we have, by his calculations, 324 joules produced and 0.09 watts consumed. At this point, the COP that results is 244, but we have consumed this energy only for 3/7 of the time. So assuming that it was the 3/7 is the half, the COP is double than this. So it will be 488 approximately.
Let me emphasize that the consumed power is the power consumed by the resistor.
Is the power that has been
by the resistor, the 1 ohm resistor.
Yes.
Whereas the power consumed by the reactor is an assumption that it has zero resistance, so it's much lower.
Yes, exactly. And to clear this point, we have made a dummy with 800 ohms and with 1 ohm to check that the resistance of that. Two things we have checked. First, that we have not a fixed amperage source, because the amperage is changing the resistance. And second, that we have not an appreciable resistance in the cut, because when we have joined the two cables bypassing the ECAT, we have found the same order of magnitude of current.
And this is 1.4 times delta T.
Yes. No, this is already included there.
Yeah.
Yes.
It's just another.
Yes. Yes. In effect, the ratio should be a little bit more because we did not multiply by 1.14 to pass from joules to watt hours. But okay, let's say that we got a COP between 400 and 500. That's enough, I think.
Now, we're really late at the program. There is a refreshment outside. Could I just ask you two questions as a conclusion of today's session, Andrea? So just some your plans now. As far as I understand, you feel quite ready to go from a kind of research prototype to start production of commercial products. So what are your plans?
Well, the apparatus that you have seen today is obviously not an apparatus ready for an industrialization. Here are many problems to be resolved. The problems are the miniaturizing of the control panel, and the problems are also the study of massive production systems. We are already in contact, as I said, with big concerns, and we are convinced that we are in the track to arrive to make a massive industrialization about this apparatus, at least for what concerns its ability to produce heat able to be converted into electricity for various kind of utilization. I want not to enter in the details of these utilizations because I want not to give now a suggestion about which are the concerns we are in contact with, because we are under strict NDA situations. So we surely will develop the industrialization of this technology. We have individuated in the United States and in Sweden the starting point of this activity. We have also to continue, as you have understood from the prolusion of Carl Oskar Gullström, we have to continue also a research under a theoretical point of view, because I am convinced that this research will have a synergetic effect with the development of the industrialization.
So thank you. Just very concrete questions about the runtime that you expect from one reactor without refueling. How long time is that?
Well, I am sure of at least 6 months. I think that it will be possible to arrive to longer periods, like, for example, 1 year. I am sure about 6 months, and yes,
and
minimum 6 months is reached.
And at refueling, you basically just change the reactor, is that so?
Yes, yes, because they are too small to be refueled on site or by the customer. So we think we will organize the situation, but maybe it will be different. I don't know. In this moment, I think that the best thing is just to take off the old let me call them cartridges. They take off the used cartridges, substitute with new cartridges, and recycle the used cartridges. One advantage of ours is that we use only easy to be recycled materials. We do not use materials that are not recyclable. And not only they are recyclable, but all of them have been chosen and selected also to be recyclable intrinsically, so inside our own production. So basically, the nickel that we use, once it is no more good, it does not need to be sent as scrap nickel to some foundry. It will be used by ourselves to remake a material, a nickel that is ECAT grade.
And in a commercial module, is there a minimum amount of reactors clustered together that you think will be the typical model?
Well, today we clustered three modules. The issue, yes, is fundamental. Our objective is to arrive to the fact that with a control system as big as a cigarette packet, we can connect at least 100 modules, maybe more. I hope much more. I am thinking as a model to the evolution of the microprocessors, that we started from computers that were as big as this room, and now this thing here is more powerful than the ones that were as large as this.
Do you also have an estimated cost per installed kilowatt?
This is very difficult because the answer should not be a number but an integral. An integral in which you have a time in the axis and technological development in the y's. So it's impossible to answer. But what I can say is that we are already now in an order of magnitude that is in an order of magnitude below the actual costs of energy and power. But I am convinced that that there is an enormous room of improvement.
Thank you, Andrea. It's been a long day, and any questions? I'm convinced that most of you have lots of questions, and it will be possible to send these questions to your blog, right?
Yes. Now, I beg you to explain to them all the places where they can put questions. Another thing, persons that are here that want to have an one-to-one with me for some reason can come. The organization of this conference has been so kind to allow me to have an office. Later you will explain me where. Yeah,
it's outside here, room next.
Here in this.
Yep.
I will be there, and I will be at your disposal. Just please consider that I cannot dedicate more than 10-15 minutes to each of you, but later, so we can start a contact that then you can develop in the internet and etc. Anyway, I will be there to. By the way, I will be also together with my friends and commercial licensees for Sweden and other countries of hydrofusion that are here. And so the Swedish people that is here that needs contact for something can also contact directly them here. And that's it. That's it. Just explain all the yes, you can send to my blog the questions, but not only to my blog.
Yeah, you will be able to send questions to the Journal on Nuclear Physics, which is the blog of Andrea, and also at ecat.com, I think. Not at the moment to my blog. I will not be ready to answer questions there. but certainly your blog. And I would say that now we will have time for some refreshments. Finally, I think we need that after this day. And there is some refreshments served upstairs where you had coffee this morning. So thank you very much again for coming. Thank you for coming to Stockholm, Sweden. And thank you for your patience with this long day. That was a little bit longer than we had expected.
Thank you, man.